Hi again. So now we're moving on to yet another module. Previously, we covered the concept of spatial autocorrelation in abstraction, and we focused on the spatial weights. Now we're going to look at two specific measures of what I call global spatial autocorrelation, to contrast it with local spatial autocorrelation, which is the cluster detection. So we're going to look at two specific statistics. One is Morans I, arguably the most commonly used spatial autocorrelation statistic. The other one is Geary C, which is a little less known, but therefore not less useful. And just to recap, what do we mean by a global spatial autocorrelation measure? We saw this a couple of modules ago, that a good spatial autocorrelation statistic combines a formal measure of attribute similarity with a formal measure of locational or geographical similarity. And we saw earlier that the latter, the second part, is the spatial weights. Very important, a global, and that's why I stress this, the contrast between global and local, it's one statistic for the complete pattern. So the global statistic is a test to reject the presence of spatial randomness in favor of clustering or negative spatial autocorrelation, but it does not identify clusters. And that's important to keep in mind before we move into local spatial autocorrelation statistic. And the reason I mention this is that there's often a misconception, is that when you find a positive spatial autocorrelation coefficient, you start looking at the map and saying, oh, there's a cluster here, there's a cluster there. You actually can't do that. All the autocorrelation measure says is that there is no spatial randomness and this evidence of similar values grouping together in space. Similar may be high, maybe low, or maybe both. We'll get back to this later. So let's start with Morans I. Morans I has been around since 1948. It's arguably, as I mentioned, the most commonly used spatial autocorrelation statistic. Most people, if they know something about spatial autocorrelation, it's Morans I. And it's popular because it looks a lot like a Pearson correlation coefficient, but that doesn't mean it has to be interpreted as such. It looks a lot like Pearson because, if you recall, attribute similarity, a measure, a function, and spatial similarity. The attribute similarity that we saw a couple of modules ago was the cross product, and that is what Morans I is based on. So here's a statistic. It's a mouthful, but let me go through it piece by piece. We have a double sum. Remember the pairs, sum over all the pairs of I and j, of the neighbors. So this looks like a very complicated expression, but keep in mind that when I and j are not neighbors, this is 0, so then it doesn't count at all. So only for those neighbors where the weight is not 0 do we count the cross product of the values at I and j. For z, where z is the observation and deviation from the mean. So first, we rescale our observation, and in fact, we center them on 0 so that the overall average is 0. We subtract the mean from them. So in the numerator, we have this double sum of the cross products of the neighbors, so to speak, divided by this factor, and S naught, as it's called in the literature, is actually the sum of all the weights. And remember what I mentioned the other day about row standardizing the weights. When you row standardize the weights, the sum of all the weights equals the number of observations, or n. And look here, we have the same n in the denominator, so these will cancel out if we have row standardized weights. The denominator should look very familiar. These z's are deviations from the means. The sum of the square deviations from the mean divided by the number of observations is a measure, an estimate of the variance. So basically, we can think of a correlation. Pearson correlation coefficient would be the cross products and then divided by the product of the standard deviations. Here it's an autocorrelation, correlation with itself. So the cross product pertains to different locations, but the same variable. Because it is so similar to a correlation, a Pearson correlation coefficient, it's often it's often the autocorrelation statistic that is used, but that doesn't mean it's necessarily the most powerful or the most insightful. It is related to a linear relationship between the value at a location and its neighbors, something that we'll revisit in the second set of slides, where we'll look at the visualization of global spatial autocorrelation. So here's Morans I. We have the numerator with this cross product for the neighbors scaled by something, and the denominator, the variance, basically the sum of square deviations scaled by something. And look at it a little more closely at these scaling factors. As I mentioned, this scaling factor in the numerator looks very unfamiliar, but in essence, what we want to scale by is by the number of expressions that matter. So for example, for the variance, we have the number of square deviations, we sum them all up, and we divide them by how many there are. And so, since we have n observations, the sum consists of n elements, we divide it by n. That's a no-brainer. In the numerator, what do we divide by? Should we divide by n? No, because we're talking about pairs of observations. Should we divide by n squared? Well, maybe, except, remember, most of these WRJs are 0. That's the whole point of using a weights matrix to put constraints on the interaction. Recall that was a very important motivation for having the weights in the first place. You know, if we have interaction data, we don't have to do this, but we actually only have cross-sectional data, so we do have to do this. And as a result, there's really no point in rescaling by n squared, because a lot of these cross products are multiplied by a wij that is 0, so they don't count. How many of them count? The number of neighbors of weights that are non-zero. So that's the motivation for rescaling the numerator by S0, the number of weight, the sum over all the weights, and we scale the denominator by n. As I mentioned just a minute ago, if we use row standardized weights, then each of these row sums is 1, so we have n of these row sums, so then both numerator and denominator are scaled by n, and they cancel out. Okay, so we have our statistic. Remember, that was the whole point. How do we compute something from the data that allows us to infer whether spatial randomness holds or not? So how do we figure out whether this particular computed value is significant, in the sense that it would be it's extreme with respect to the reference distribution, which corresponds to spatial randomness. Now, in the early literature, this was done analytically, and I already alluded to this earlier, that these analytical expressions are extremely complicated, and in fact, typically they use approximations. So one approximation of spatial randomness, even though it has nothing to do with the spatial part, is to assume that the variable is normally distributed. And then for a normally distributed variable that is spatially random, one can compute what the mean of the Morans I statistic would be, what its variance would be, and then using another approximation, we can compute a z statistic and assess its significance. So those are the analytical derivations. I don't want to spend too much time on them, because, as I mentioned earlier, it is so easy to do this computationally. We saw that spatial randomness can easily be replicated by reshuffling the values. And since we have fast computers, why not do it that way? And then we don't have to make any assumptions, because the data give us the reference distribution just by reshuffling it. Another reason why I don't want to spend too much time on it is that the analytical derivations are actually very confusing. One is very straightforward. You assume normality and then you compute these means and variances. I remember in graduate school I had to do something similar to that for the Durbin-Watson statistic. Those of you who've taken econometrics might recognize the shape of Morans' eye and the shape of the Durbin-Watson statistic is very similar, but it's very complicated. Another assumption that you see in the literature is unfortunately called randomization. And randomization in essence means equal probability. So there's no assumption of normality, but there is the assumption of equal probability for any value to fall on any location. And then using that framework, you can again derive what the mean and the variance would be and do an approximation with a z value. So just to give you a sense of what that means, in the next slide I'll show you an empirical example. But the z value is very important because, I mean, I made it explicit, but the mean is the same, but the variance that you get in the analytical approach for the normal approximation versus the randomization is not the same. So these, in essence then, these statistics are not comparable. And in addition, I haven't even mentioned this, but remember the importance of the weights, which means that the statistics become very difficult to compare. You always have to take the statistic with the weights together. And to get around that, we construct a Moran z value. And the Moran z value is simply a standardization where we subtract the mean and divide by the standard deviation as computed from the reference distribution. Of course, if you have just a single statistic, you don't have a mean or a variance. You get the mean from either the normal assumption, the randomization assumption, or what I call the permutation, the computational implementation, where you reshuffle the data and get your reference distribution that way. That reference distribution has a mean, has a variance, then we use those to construct a z value. Now, because these z values already incorporate the complication of the spatial weights, they are actually comparable. So in any situation where you have different spatial weights, the same variable or different variables, the Morans' eye coefficient as such is not comparable. But after you standardize it into a z value, then it becomes comparable. And I'll get back to that with the illustration in a few minutes. So this is an example in the lab notes. We have similar examples. These are the house prices in Cleveland that you used in the lab notes to compute distance-based weights. So there's a distribution. What we're interested in finding out, is this distribution random or is this distribution somehow spatially structured? Remember, we're not trying to find the location of the clusters. We're just trying to assess whether there is clustering or not. So we have these house sales. What we're looking for is, are there situations where there's groupings of the blues and the reds and the browns, more so than would be the case under spatial randomness. Okay, here's the analytical approach. So Morans' eye obviously is the same value, 0.28. The mean of Morans' eye under the null hypothesis of spatial randomness is analytically -1 over n-1. We'll get back to that in a second. So essentially a little bit negative of 0, but as the number of observations increases, as n becomes larger and larger, then the difference between n and n-1 becomes negligible. So that analytical mean is minus 0.0049, and if you know the number of observations, you can compute it exactly. So far, so good. The variance is where it starts to make a difference, and using the normal approximation, we get this variance of 0.00178. Using the randomization analytical derivation, we get 0.00158. So the variance is smaller for the randomization assumption than for the normal assumption. As a result, the z-value, which we get by subtracting the same mean, but dividing by the variance, since this variance for randomization is smaller, the resulting z-value will be larger. Both of them are highly significant. And because we can compare the z-values directly, we would say there's stronger evidence under randomization than under the normal null hypothesis. Of course, it's the same statistic, so this can be confusing if one approach says it is significant and another approach says it's not, which can happen. As I said, my preferred approach, and the one that's implemented in GeoDa, so purposely, GeoDa reflects a lot of my personal biases, and I really don't think it's a good idea to do these analytical derivations because the assumptions are too strong. And this day and age, you have the computation, so why not use it? So the permutation approach, we compute our reference distribution ourselves. And then from that distribution, we compute what the mean is and what the variance is, and then do our standardization based on that. So that's basically a brute force approach where we get our reference distribution. And this is what it looks like. So here are 999 randomly reshuffled data sets, for each of which we computed Morans I. And on average, the Morans I is minus 0.0045. Remember, here analytically, it's 49. So because we're simulating, it's not exactly the same, but it's close enough. And then we have our standard deviation and our empirical, if you wish, z-value, again, highly significant. You don't actually have to compute a z-value because you can see here is our actual Morans I of 0.282, and this is the distribution of the 999 empirically based Morans I, the largest of which was not higher than 0.2. So we have quite a range. We have the central tendency, just a little bit left of 0, and then based on the characteristics of this, what we call the reference distribution, we can conclude that the actual value of Morans I of 0.282 that we computed is highly unlikely to have occurred under a situation of spatial randomness. So we reject the null hypothesis of spatial randomness. That's really the bottom line. So what does this all mean? First of all, the sign of Morans I, lucky for us, it's not always that way, as we'll see in a few minutes. Lucky for us, when Morans I is positive, it means positive autocorrelation. When it's negative, it means negative autocorrelation. The mean, as I mentioned, the theoretical mean is -1 over n minus 1, which is basically 0, just a little bit negative of 0. Very important, we only conclude that there is clustering of like values when the Morans I is positive and significant. If it's just positive, that means nothing. That means there isn't enough power, there isn't enough evidence to reject the null of spatial randomness. So one mistake people often make is that they still refer to it as positive spatial autocorrelation, whereas in fact it should be referred to as spatially random. So unless it is significant, the sign doesn't matter. The sign is irrelevant because it is, for all practical purposes, spatially random. So then the opposite is negative, and significant, that's alternating values. That's not the clustering. Very important, it's clustering of like values. It's not high or low. It could be high or low or both. There's an example in the literature of a misinterpretation of Morans eye. It has to do with the stroke belt. The stroke belt is a region in the south and east of the United States where there for years, for decades, has been an elevated incidence of strokes. And some of the early spatial analyses of this phenomenon at the state level computed Morans eye and concluded that because it was positive and significant, that there was a clustering of high stroke rates. As it turns out, and we'll see in the next set of slides how we can assess that, in fact, the high positive and significant spatial autocorrelation Morans eye was driven by a clustering of low values in the Midwest and upper Midwest of the US. So it's not because it's positive that it's high, because if it's positive and significant, it means similar, high, low, or both, some mixture. When it's negative, it's always the same thing. It's the alternating pattern, could be spatial outliers, could be spatial heterogeneity, checkerboard pattern. It's a little harder to interpret. Positive and clustering is easy to think about. Negative and checkerboard is a little harder to think about. Secondly, as I've already mentioned, the Morans eye as such depends on the spatial weights that are being used. So their strict value, once you use different spatial weights, cannot be compared. You use the same weights, different variables, you can't compare them. You use the same variable, different weights, you cannot compare them. But what you always can compare is the standardized z-value. So when you do your assignments, when you do your analysis, and you are assessing whether one or another variable is more spatially correlated, don't look at Morans eye as such. Always focus on the standardized z-values. Those are the only statistics that are comparable across variables and across weights. Just to illustrate this, this is now based on our permutation approach, our computational approach, and I have used 3 different kinds of weights. Queen, contiguity, based on the tessellation of the points. In the lab notes, we go into more detail. The lab notes from the previous module, we went into some detail on how that works. K, 6 nearest neighbors, and then a distance band nearest neighbors. So if you would look at the Morans eye, the same variable, house prices, you might say, well, the strongest evidence of spatial autocorrelation is found for the 6 nearest neighbors. The means are the same. The variances are different because of the different weights that are being used. The z-values are also different. And so here we are with a z-value of 10.3, whereas the original Morans eye was the second highest. So the Morans eye is the highest for 6 nearest neighbors, but actually the z-value is the highest for the distance weights. And I need to correct myself. These are actually based on analytical derivations, not on the permutation, if I remember correctly. But the main point is here, don't focus on the value of the coefficients. This is very different from interpreting a Pearson correlation coefficient. If you have a Pearson correlation and you have 0.6 and you have 0.2, 0.6 is always more correlation than 0.2. For Morans eye, that's not the case. It depends on the weights. So in this case, you might say 0.34 is more than 0.33, but in fact, it's not. This distance-based has a higher z-value. So keep that in mind. That is very different from standard statistics. A couple more interpretation issues. clustering versus clusters, and I cannot say that enough because over and over again I see this misinterpreted. Morans is a global statistic, as I mentioned. It's a single statistic for the whole pattern. It does not tell you where the clusters are. As much as you may be tempted to conclude from a positive Morans global Morans that here's a cluster, there's a cluster, you can't do that. All you can say is you reject spatial randomness in favor of a structuring of the data, either along the clustering lines, which is positive spatial autocorrelation, or along the the checkerboard lines, which is negative spatial autocorrelation. To find the location of a cluster, we'll need a local statistic, which is the topic of the last two modules. Then another very important thing is how to interpret this. So what does this clustering mean? And here again, a major misnomer. Many times the presence of significance positive spatial autocorrelation or clustering is interpreted as contagion, as innovation, adoption, something of that kind. Actually, you cannot make that conclusion in a cross-sectional data set. If you don't have the time domain, you cannot make that conclusion, and that's an example of what is called the inverse problem. And the inverse problem has to do with the difference between pattern and process. I alluded to this before in the exploratory data analysis. We can find associations, but we do not find causation. Same here. We can find patterns, but we don't know which processes actually yielded these patterns. So we know the pattern, but not the process. And as it turns out, spatially clustered observations can occur as the result of two very different processes. One is called true contagion. That's a result of spatial interaction, peer effects, mimicking, the kind of thing you see in contagion with the flu or with COVID. That is, one person has it, gives it to the next person. And so they all went to the same party, so then you have a cluster of people with COVID or with the flu. But we don't know that. We don't know the process. What we observe is a data set where the group of locations that have COVID. And so we conclude it's not spatially random, it's clustering, but we don't know what caused it. And specifically, let's just take the COVID example, and let's say we had a group of people that, they shouldn't be doing this, but gathered in a small room, and we find after the fact, and in fact, there is a cluster of COVID. We don't know whether this is because one person in the room had COVID and spread it directly by contact to the others, or whether this room was already contaminated and the people went into the room and got it from what was hanging in the air. That is a case of spatial heterogeneity. The air in that room is different from the air outside. You can have another example, and this comes up time and time again in disease situations. Is it actually a contagious process, or is it because something is different? For example, the groundwater is polluted, or something along those lines. And you can also think of other processes where it's either a structural difference. So a structural difference would be different quality soil, pollution situations, systematic racism. These are structural differences that could result in clustering of poverty or crime or disease, for example. Or it could be a social contagion process where one gang member comes into the neighborhood and gets the neighbors, neighbor kids riled up to join the gang. So you get a cluster as a result of an interaction process. So without further information, the clustering in a cross-sectional setting does not provide you information about the interpretation. So what I do not want to see in your assignments is, after you decide that there is evidence of clustering, that you then conclude there is spatial interaction. Maybe, but it could also be spatial heterogeneity. This is the inverse problem, the difference between true and apparent contagion. Very important to keep in mind at the time where you write the interpretation of your analysis. So that's Morans' eye. Geary C is a slightly different animal in that it no longer uses a cross-product statistic, but it uses the square differences. And if you recall, when we discussed attribute similarity or dissimilarity, we had on the one hand the cross-product, and on the other hand square differences and absolute differences. And the square difference is similar to what is used in geostatistics. I won't really dwell on that in this course, but some of you may have heard about this, of the variogram, which is a way to measure spatial autocorrelation. That's also based on square differences. The values of Geary C are not positive and negative, but they go between 0 and 2. Roughly, the difference, big difference between Geary C and Morans' eye is, recall, the mean for Morans' eye under spatial randomness was just a little bit negative from 0. The mean for Geary C is 1, so not 0 at all. So here's a statistic. It is not quite as old as Morans' eye, but still pretty old, a paper in 1954. The numerator is our weights again, but now instead of the cross product, we have the square difference. So all these spatial autocorrelation statistics look very similar. They're a double sum over all the pairs. Remember, it's about interaction of the weights. But also remember, most of these weights are 0, so these things are only counted for the neighbors. And then we have some scaling factors. And the scaling factor for Geary C, you can look at it slightly different here. I've written it here to keep the similarity with my notation in Morans' eye. Again, we have this S0, the sum of all the weights in the weights matrix, and we have here n-1 instead of n, which is an unbiased estimate of the variance. These z's are deviations from the means. These don't have to be deviations from the means. Think about this for a second. Why would we not have to subtract the mean? Because if you subtract it from both, because of this subtraction, they cancel out. So the numerator can be in the original variable or in deviations of the mean. It doesn't really matter. The denominator has to be in deviations from the mean. And as before, we keep the same scaling factor. So Geary C statistic is a little bit weird. The mean is 1. So positive spatial autocorrelation is a value smaller than 1, or a z value that is negative. So positive spatial autocorrelation is a negative Geary C. Why would that be the case? Well, before we had similarity. So positive is similar. Here we have dissimilarity. So small is similar, large is dissimilar. So because a small square difference will give us a negative Geary C, positive spatial autocorrelation actually matches a negative sign. Negative spatial autocorrelation matches a positive sign. So it's the opposite of Morans' eye. Now, to some people that seems very counterintuitive and kind of weird. If you're uncomfortable with it, just change the sign, and then it's the same again. Then you say negative C is positive for positive autocorrelation, and negative C is negative for negative spatial autocorrelation. As long as you remember that it's the opposite of Morans' eye, and it is the opposite of Morans' eye because we're not measuring similarity, we're measuring dissimilarity, difference, square difference, in fact. So again, Inference, same deal. We can go the analytical route. It's even more complicated than Morans' I to figure out what would be, we assume normality, we assume equal probability or randomization. We figure out analytically what would be the mean, 1, what would be the variance, difference between the two assumptions, or we can say, forget this, let the computer do the work, and we do the randomization, the permutation, same way as for Morans' I. Same issue. Let's here again analytical derivation. We have the Geary C for queen contiguity, 6 nearest neighbors, and a distance band. Keep in mind this is relative to 1, so less than 1 is positive spatial autocorrelation. The smaller is, at first sight, the stronger. But remember, just like with Morans' I, we can't just focus on the statistic as such. We have to focus on what happens after we take into account the different variances for the different weights. And then, just like in the previous example, we see that the distance band indication is actually the strongest indication of positive spatial autocorrelation under Geary C. So again, it's not the statistic as such. You have to keep the statistic together with the weights, and the only way to do that properly is by standardizing the statistic into a z value, which we see here. The randomization, same idea, but now our significant value will be on the left side because it's centered on the mean, and here we see the mean is almost 1 in our 999 permutations, and we compute the variance. This gives us an empirical z-value, but again, just like in the previous example, there is nothing that comes even close to the values that we get under randomization. So the value of 0.716 that we obtain empirically is so extreme relative to the values that we would get under randomization, under spatial reshuffling, that we clearly conclude that we can reject the null hypothesis of spatial randomness in favor of positive spatial autocorrelation. Why positive? Because the Geary C is less than 1. So this kind of concludes the formal part of this module. We've seen Morans' I, which is a cross-product statistic, and Geary C, which is based on square differences. Morans' I is centered roughly on 0, so positive values are positive spatial autocorrelation, negative values are negative spatial autocorrelation. Geary C is centered on 1. Values less than 1 are positive spatial autocorrelation. Values larger than 1 are negative spatial autocorrelation. For both of these, the recommended inference is to use computational permutation approach, where we just compute the reference distribution by reshuffling the values and then compare what we have observed as Morans' I or Geary C to that reference distribution. And finally, very important, and I will repeat it multiple times, the fact that we find spatial autocorrelation, significant spatial autocorrelation, only pertains to the pattern. It does not pertain to the process. So we cannot conclude from positive spatial autocorrelation that there is an interaction going on. It could also be spatial heterogeneity. Been a long day. So keep that in mind, and in the second set of slides, we'll deal with the visualization of global spatial autocorrelation. See you then.